In this question, we'll practice calculating electric field from a point charge, but we'll also practice vector addition as well, all the way back from Unit 1 and perhaps even grade 11. We don't want to forget our vector addition. So what's happening is there are two charges here. I drew them in as red and blue, a positive charge and a negative charge. So both of those charges are creating an electric field all around them. So they each create their own field lines, and we can calculate the net electric field by adding the two fields together. At any point in space, we can do that. We're going to focus on point P. So I'm simply going to calculate the field created by the red charge at point P, and then I'll calculate the field created by the blue charge at point P, and then I'll add the two together. But I have to add them in vector addition because, well, they're vectors. Okay, so let's start with the red charge. The red charge, it's a positive charge, so it will create an electric field that's to the right. I'm going to call that E subscript 1, standing for the first charge. I know it points to the right because it's going to point directly away from a positive charge. So I'll calculate the value of that with the formula for electric field, which is KQ over R squared. I'm going to just use K to two significant digits here, just to save myself a little time and space with writing. 9.0 times 10 to the 9. That's Coulomb's constant. Q, the charge of the red charge, is given as 1.0 times 10 to the negative 10. And then R, the distance away from the red charge is 1 meter. So 1.0 squared. So actually, I don't need a calculator for this because it's 9 times 1 divided by 1 squared. Well, that's just equal to 9. But I will have to figure out my power of 10. So let's see, I have 10 to the exponent 9 times 10 to the exponent of negative 10. That makes 10 to the exponent of negative 1. That would be newtons per coulomb. Now, I don't think I need scientific notation for that. I can just write it as 0.90 newtons per coulomb. Now, with the direction, it's to the right. Or I can say east because the question does talk in terms of west and south. So we're using compass directions here. That will be east. Now I'll calculate the electric field created by the blue point charge. The blue point charge is negative. So the electric field will point towards it because it would attract any positive test charge placed there. So it's going to be south. I'm going to calculate the value of it. Same formula. Just apply the blue values. I'm going to put positive 3.0 times 10 to the negative 10. It is a negative charge, but this formula is only calculating the magnitude of the electric field. I'm going to put all positive numbers in there. And the direction is taken care of. I drew in the direction already. I already know the direction. The distance that the blue charge away from P is 2 meters. Okay, so I'll calculate this out. This will be 9 times 3 divided by 2 squared. So 9 times 3 is 27. 2 squared is 4. So it's 27 divided by 4. That's 6 3/4. So that's 6.75. And then the power of 10, I've got 10 to the 9 times 10 to the negative 10. That makes 10 to the negative 1, which is consistent with the red one. So we're approximately the same size here. We don't have one that's way bigger than the other one. And the direction is going to be south. I'll rewrite a new line without the magnitude bars. So the electric field created by the second charge is going to be 0.675 newtons per coulomb south. That'll be to two significant figures, so I'll underline two significant figures. So those are the two electric fields, and I want the net electric field. And I want the net electric field. That's what the question is asking for. Net just means you add them together. So the net electric field, E net is what I'll call it, will be electric field 1 plus electric field 2. They are in perpendicular directions. So the best way to do this is vector addition, would be to draw a triangle. So my first value is 0.90 newtons per coulomb, what I calculated for the red electric field. And then tip to tail, so from where I left off, I now add on to it southward vector, and we calculated 0.675 newtons per coulomb for that. And what I'm trying to find is the hypotenuse. Okay, whatever the hypotenuse is, that's going to be the net electric field. And I'm going to want to know the direction of it as well, so I'm going to label the angle theta. The net electric field in magnitude, that'll be solved by the Pythagorean theorem. That comes out, when I round it to two significant digits, 1.1 newtons per coulomb. And the angle will be the inverse tangent of opposite over adjacent, so 0.675 over 0.90. And I'm getting 37 degrees for that. So my net electric field will be 1.1 newtons per coulomb, and then it will be east 37 degrees south. Okay, so a little practice with the electric field formula, but also a little review of vector addition. Part B, so that was the answer to A. Now B, if we were to place an electron at point P, what force would it feel? So the electric field tells us how many newtons 1 coulomb of charge will feel. It's 1.1 newtons per coulomb. I probably should have kept a couple extra digits there, but too late now. I already cleared it from my calculator. Oh well. But it's more important we understand the concept that this electric field tells us how many newtons 1 coulomb would feel if placed in that location. So what if we were to place an electron at that location? Well, an electron is not 1 coulomb, but we know how many coulombs it is. So we can find the force just by multiplying our electric field by how many coulombs we have. The concept we're trying to get across here is that the net force, you just take the charge of whatever particle you're going to put there and multiply it by the net electric field. So the charge of an electron turns out to be negative 1.60 times 10 to the negative 19 coulombs. We're going to multiply that by 1.1 newtons per coulomb. Preserving our direction of east 37 degrees south. But notice how I did put in the negative for the charge of the electron, so my answer is going to be negative. That's going to actually just cause the direction to flip. It'll feel a force the other way. So let me multiply this by 1.1 first. So the force is going to be negative 1.76 times 10 to the negative 19 coulombs, east 37 degrees south. Or if I want to write it as a positive force, it's the 2 sig figs, by the way. If I want to write it as a positive force, I can do that. Just have to flip the direction. So east 37 south becomes west 37 degrees north. East flips to west, south flips to north. And that would be the force that an electron would feel. So going all the way back to the diagram here, when I add up my red and blue vectors, I end up with a diagonal vector. That's east 37 degrees south. That's the net electric field. If I were to put a positive charge there, that's the direction it would go. But I'm putting a negative charge there. I'm putting an electron there, so it actually ends up going in the opposite direction, which is west 37 degrees north.